Two. I'm going to do a midterm review, and I'm basically just going to go through the test. Hopefully it isn't too ugly. I was trying to do it really fast. I did okay, but I didn't get everything right. So lesson in that, definitely, if you have the time to check your answers, you always want to do that, even if you are kind of flying through at a quick pace. So I'll try to moderate a bit, but I'm probably not going to check as thoroughly as I would if I was you, because you don't want to watch me sit here and go through all my answers. But I'm not going to do the roll call today, so sorry about that. That's just some old stuff. So homework 4 is long term, due at the end of the semester. Don't forget about it. You want 7 out of 8 good homework grades one way or another. So really there's a lot of flexibility in there, but you might want to just take a look at 1 or 2 of those. So midterm practice is available, of course. You might want to take a look at that before the exam on Thursday. It's going to be very representative of the test. I don't generally change things unless I get feedback from you. So a lot of times I'll look at if people have taken the test and it's taken too long, or they get something really wrong because maybe the wording is unclear, I'll go update that question. So I do try to give back. If you take the practice exam, I'll look at how everybody did and then use that to help tune the test, usually in a way that benefits you. So that could be a helpful thing. So it is open book, closed human, no AI, all that good stuff. You will need to be on the school computers. So please, you may bring your laptops. And I did make a decision. You can use some folks do have notes on their laptops. So I don't want to be too heavy-handed. So you can use your laptops for reference if you have notes, but you know, if you are doing a lot of chatting and all that stuff on there, then it's a little problematic. So please use that wisely and fairly, and I don't think it'll be a really problem for anybody. The other thing I do is I will run a Zoom chat. So you can go to the syllabus page either now or 10 minutes before class and jump on chat, or do it in the middle of the test. But, you know, sometimes you do it in the middle of the test, it gets, you know, you get frustrated. And the purpose of this is so if you find a problem with the quiz, or you think there's a problem with the quiz, then you can say, hey, I think there's a problem with question number so-and-so, and we can have a quick exchange where I can check it. And maybe there'll be a problem, or maybe it'll just be like, hey, I think you need to take another look. Either way, it stops us from having a dialogue at the desk, but it allows me to help you kind of maybe see what I want you to see. I will not be giving anyone answers over chat, so you don't have to worry about that, but it does just help keep the distractions at a minimum. So if you feel like you need to chat, please try Zoom first. And if for some reason you can't log in, well, then we'll sort of take it from there. Okay. You can, of course, use Replit or ProgramIZ or Visual Studio Code. Now, I know some of you are using VS Code on your own platforms for coding. Sort of blurs the lines a little bit from my intentions. I don't want to punish folks who don't have Visual Studio Code available on the school computers. So if you're using Visual Studio Code to program fragments of code on your own computer, I'll allow that. But again, I just want the canvas to be on the school computers. So we're kind of all in that window frame working on the test. So hopefully that gives everybody fair kind of access to the tools you need for the test without it getting too crazy. Questions on that part? Yes.
Are we logging into Zoom?
Yeah, so I'll need to be running the meeting. You don't have to do it right now, but if you did do it, you know, I'll see you and I'll add you to the chat, and you'll just be able to chat with me during the actual class. So if you've never found that link before, you might want to actually just look at that and see, but I won't add you guys right now. So I think you guys know what everything is covered. We'll have about just under 3 hours. If you get here a little bit late, you know, you can end a little bit late. It's when you start the Canvas quiz that the 170 minutes starts counting. I'm not going to kick people out here at 8, But if you get here like half an hour late and I'm here till 8:30 and everyone's gone, it's getting a little bit past, reasonable. So I'm okay with a little bit of overage if you get started a little late, but do try to get here on time. About 50 questions. I think it's going to be quick. If you haven't done it, you're going to maybe find that it's really, there's only a couple questions that you need to sit down and really double check or triple check. And there are multiple types. I got burned today on a multiple select all that apply kind of question. So watch out for the different types of questions. They do kind of sneak up on you. I think the rest we've probably talked about. You will not see corrected answers until Friday, which I know is a little annoying, but I just need time to kind of, fix anything that's broken. So I'm not regrading everything multiple times. Every once in a while, there's a broken question and I got to go around and give everybody the proper credit. So that just gives me a little time to be fair and, make sure everybody's accounted for before you see your grades. And I got to grade the essay questions too. So I just need a little time for that stuff to be on. So you got to be in class. Please don't forget. I'll send out an announcement reminder. No redos on this one. So got to have everybody in class. Okay. And for folks, well, I'll just leave it there and then I'll circle back with people later on. Okay, so covering all this stuff, we've talked about this all the way through the word, descriptions, asymptotic analysis of lecture 4. So hopefully you had a chance to look at that video if you weren't actually in the room at that time. Okay, and there's about one to two questions per topic, but more ones than twos for sure. So I think you probably have a sense of what that is. Okay, so let me just switch over to the actual quiz and see if I can do this without completely blowing myself up. I've been getting a little better at it, but it's a little bit intimidating to talk and take a test at the same time. So, but it is my test, so I should be doing better than not. Now I'm going to zoom up a little bit with my Control Plus keyboard moves. That's going to make some of these questions all smushed up. So, that's just for your kind of viewing in the classroom here. So you can do that or not do that when you actually take the test. So first one's a throwaway, right? You're not going to get penalized. I'm not even going to penalize if you give me an answer I don't like. It's just sort of making the point one last time. And then we're off with the logarithm. So what is the base such that the exponent gives me a 4? That's going to be a 4. 4 to the first power gives me a 4. So that's my logarithmic answer. And incidentally, I'm probably going to make some mistakes on these. So I'll pause. If you see anything wrong, please feel free to shout it out for everyone's benefit, because I'd hate to, give you the wrong answers on this as I'm going through, but I do sometimes make mistakes. Okay, so sorting algorithms. These are always the clues up top, of course. What is this thing doing? Okay, well, it's not exactly sorting anything. It's doing a comparison, and it's returning false in the middle of a for loop. That means it found something bad. So what is the bad thing? Well, if something at a position I is greater than the thing before it, then that means that we are increasing. And this must be that increasing is a bad thing. So that means that we're probably looking for an array that is sorted in descending order. Okay. So if A is greater than B, and that's then A minus 1, A of I minus 1, and that's a bad thing, then that means that's increasing and we must be looking for decreasing. So I'm going to go with that one right there. Stop me if you think I'm wrong on that one. I think I got that. Okay. All right. So, and performance matching terms of equations. Just want to know if we can kind of look at equation and sort of fuzzy it up a little bit. Which of these is quadratic, right? In the quadratic family. So that's going to be somewhere where we have, an n squared term. So if we factor that all out, of course, we're going to find that that's an n squared term. I think I need to make that even a little bit bigger. I know you guys are really looking from a way back there, so sorry about that. There's our n squared term, and I'm going to go with that as our quadratic answer. Average number of swaps. So these are a little tricky because averages is not really an asymptotic thing. It's not a worst case, best case. And a lot of algorithms are sort of qualified via best and worst case. But we've talked a little bit about a number of these. And so you can kind of reason some of these out. So if we are talking about the shuffle, where we're randomizing the thing, if you recall, it was kind of, there's two ways to do this. We can do it a naive way, which is really kind of like an unsort, which is quadratic. But the Newth shuffle is really a linear kind of thing. And the average, turns out, is also the worst case and the best case. It's always going to be exactly linear. So this would be an example of something we would describe as tightly bound. Its worst and best case are exactly the same. And so really this would be a big theta if we were really asking, a tricky asymptotic analysis question. But this is just basically, what do you think the average is on that thing? Well, and it should be linear, okay? Average compares for a quick sort. This one's a little trickier. So quick sort, worst case, can degrade to quadratic. Its best case can be n log n. And the truth is that the average is going to be really somewhere kind of near the n log n. That's a tricky one. You'd either have to look at some of the empirical analysis on that we did, or maybe do a little research on the web. But since we've got an open class or open notes, that's something you could kind of do some investigation on. But that's essentially where we're at. Okay. Sorting algorithms. Which performance profile below provides the best performance in terms of n? So this is testing whether you kind of get the general idea of what these equations mean. So best case is going to be the fastest sorting algorithm. So it should be something relatively small. So if we graph these curves, right, if it's linear with respect to n, that is certainly going to be less than an n log n or an n squared or n cubed. Okay, so that's really our answer right there. So you can kind of scribble or pull up Desmos if you like, but hopefully you've kind of got enough graphing, experience to kind of see that one, in the sky. And remember, we're talking about an n that's pretty big. So for all these questions, you can assume that, the graph goes way, 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 way out, and that's really the behavior we're trying to assess. Sorting algorithm code assessment. What is this thing? So if n is equal to 1, we don't have anything to do. Otherwise, we're going to pick a random number. And if it's the same as the position we're on, we're not going to do anything. Otherwise, we're going to swap. Okay. So we're not really sorting anything. And there's your big clue, of course. This is our Newth shuffle. So this is our linear shuffle. It just turns out that one popped up for me. So indeed, we can kind of see that's only going to really go around n times always, no matter what. Okay. And that's where we get our linear answer on our previous question. Okay. Sorting stability. Okay. So which of these is considered stable? This is just sort of a, rote memorization or quick research question. So the bubble sort is stable. So we're swapping things that are neighbors if they're out of order. If they're in order, we don't swap them. So that one is stable unless you implement it poorly. Insertion sort is also stable. Selection sort is not stable. We're swapping from very far away at opposite ends of the array most of the time, and that breaks our stability. Counting sort is and can be stable. So that one is a little tricky. If you go back to our lecture, we talked about that. There are certainly ways to implement the counting sort to make that thing stable. And you can also look that up too, just to kind of remind yourself. Okay. But let's take a look at our data, our example problem. So if you've got some cards, 4 of spades, 10 of spades, 9 of spades, how do we know that this, sorted like this, was a stable sort? Well, if we're sorting by the number, not by the suit, then we should never see the suit swap for equal number cards. So for example, you got a 4 here and a 10 and a 9. Okay, so we got some 9s. I got a 9S and the 9H. So if we go down here and we look at the S and the H, they're still on the same order down here that they were up there. And that's a sign of a stable sort. It did not swap these two for some silly reason. It kept them in proper order. So that would be the stable sort for that one. Okay. That is the hallmark of sorting stability. Okay, identifying algorithms. You can either read about it and think about it, or you can look at the video just to sort of prove that in theory it can be done. So let's read about this. The unsorted portion grows larger by at least one item on each pass. A lot of sorts do that. We're going to compare adjacent items on each pass and swap them with each other to achieve the correct order. The swaps are only going to swap the adjacent items, and this is the giveaway. If no swap occurs, then the entire list is guaranteed to be sorted. That's an indication of a bubble sort, okay? So I'll go ahead and nail that one as a bubble sort. But we can also see it if we run it. You can kind of see that it's going to take the biggest value and swap it with its neighbors and float that value further and further out to the right. So that 44, it's kind of just going to go one by one by one by one. So it's not an insertion sort. It's not a selection sort. It's not a counting sort kind of thing. So it's certainly not swapping from a distance. So that's pretty clearly our bubble sort friend there. Okay. One more. So performs multiple passes. The unsorted portion grows. Find the smallest, if we're doing an ascending sort, value in the unsorted portion and swap it with the value in the leftmost position of the unsorted section. Okay. So in other words, move it to the left of the unsorted section. That shortens the unsorted section and essentially grows the sorted section by one. Okay. So this should be the selection sort because we're swapping from a distance. Okay. We're not inserting and shifting here. We're swapping from a distance. And you can kind of see it here. If we play this, you'll see the red marker is kind of identifying the key that we have found. That's the smallest item in the unsorted portion. And then we're going to swap. So 3 is kind of at the far left. We're looking for something smaller. Okay. So there's our new smallest thing. So we're going to swap that with the 3 at this point as soon as we get to the end. And the 3 comes over. And this is really where we break stability. So FYI, that's kind of the aspect of the selection sort that ends up breaking stability. Okay. So that's our selection sort. So I'll go ahead and tag that one. Question 13, copy cost. These are a bear. You kind of got to really pay attention to what you're doing with these. And I might even move this toward the end of the test because everyone's taking a little more time so you don't, burn up your time at the beginning. But basically what we want to do here is just think carefully about what's the shortest path for getting these things into place. And although we can follow the patterns that we learned in sorting algorithms, like copy something out and then shift and then put something in its place, we can be even more clever than that. For example, we could, on this situation, take the position of every time I move something, I want to move it into its final position, right? So all of these things are going to have to move. And this is maybe one of the easier ones. But if I move the 7 out, then I should move the 1 into the position of the 7. Okay, so now the 1 is done. Okay, and then I can move. Actually, let me think about that. If I move the, actually, now I might be in trouble. So I'm just looking to see if there's a shorter path here. So if I pull the 8 out, let's see, pull the 8 out, put it into temp, leave open, we can pull the 2 in. Yeah, right. And then we want to find what goes in the 2. So whatever we sort of move in, what goes into its final place at the 2's position, right? It should be 4, 3, 2, 1. So we'd pull the 4 over and put it in the 2, which opens up the 4 slot. And that should be 8, 7, 6. So we can copy in the 6, right? And then pull the 8 down. Okay. So sometimes, we may not go in a straight insertion sort kind of shift pattern for that. We actually may need to do something a little more clever. Sometimes this is called cycling. So we're kind of cycling through and pulling things the correct way. So I think this one is a 9. I'm not going to work through all the numbers on that, but I'm going to take a bit of a wild guess on that. We'll come back and see if that's the exact one at the end. Um, and then merge sort. So merge sort, the thing I'm looking for here is kind of the ability to remember what merge base is doing. So remember, merge base works from the bottom up. It merges two things, and then merges those things together. So that would be 3 merges for 4 things. Okay, but let's think about 8 things. So that would be 3 merges there, 3 merges there. That's 6 plus 1, that's 7. So you kind of see the pattern here. It's really kind of rounding out to n minus 1. Okay, so if you got 32 elements, the bottom up merge of merge sort is essentially going to call merge base n minus 1 times. Okay, so our answer here should be n minus 1 if I got that right. And so you got to just think about what's happening from the bottom up there. Merge, merge, and merge, right? Slowly building those sorted lists in little chunks until we get bigger and bigger all the way up to the end. Okay? So that's our merge base function. Okay. Stacks. These aren't too hard, but they're easy to kind of get wrong because, we can't really easily print top down, although I probably could if I really thought about it. But our top is over here, bottom of the stack is here. So I push, push, push. So that's 5 on the top, then a 2 and a 1. We pop the 5, push a 3, and push a 4. So it should be 4, 3, 2, 1 for our final answer. Okay, top to bottom. Okay. So that's our stack. Priority queues. These are really tricky. This one got me today. I was in a rush. So we're asking not what's left in the queue, but what is the order of the things that were popped out. Okay. So it's a minimum priority queue. So if I push in a 20 and then a 0, the 0 is kind of the smallest thing, right? I push in a 40, pop. So the answer has to start with a 0, okay? So if I want to kind of cheat a little bit, I can kind of go down and see, oh, I got one of these 2 things. It's either going to be this one or this one. So then I push a 10 and I pop. So 10 would be the smallest thing. So it's going to be a 0, 10. Oh, yeah, as you can imagine, I kind of covered my bases there. So then I push a 5, pop. So 5 should be the next thing that gets popped. So it's 0, 10, 5. Okay. So 0, 10, 5 on those. Okay. That's our min priority queue. Okay. One more. Okay. So min priority queue. Popping is going to get the 10. Okay. The next pop should get the 20. Okay. And the last pop should get the 5. Okay. So 10, 25 looks like the right answer. Does anybody thinks otherwise? Okay. And then our Q might be the trickiest one because it's backwards. Apologies from what we did in lecture. Here I have the oldest one on the left side and the newest one on the right. So it's like we're in queuing from this side instead of this side. And I was going to change it today, but I thought you guys have already had your quizzes. I don't want to mess you up. So let's think through it. So I'm pushing in a 10. So that is the oldest, then a 20, then a 30, then a 40. So if I DQ, I'm DQing the oldest thing, okay? Then I push in a 50, then I DQ, then I DQ, okay? So I've got a 40 and a 50 in there, and the 40 is older than the 50. So it should be 40, 50, okay? I think I got that one okay. Okay, question 19. Coming up on halfway. Here's another one. So we're going to NQ10, DQ10, so it's empty, 20, 30, 40. DQ the oldest thing, right? So now we have just a 30 and a 40, and Q the 50, pop out the 30, and we should have 40, 50, right? That should be our oldest to newest, okay, for our question 19, okay? Pushing on to binary heap arrays. So we got to remember the equations. So to find the child of something, we got to multiply the position of the child by 2 and then add 1 for the left or add 2 for the right. So if I'm looking for the right child of 9, I have to go position 0, position 1. So 1 times 2 plus 2 is going to be 4. 0, 1. Let me try that again. Yeah, 9. 1 times 2 is 2, plus 2 is 4. 0, 1, 2, 3, 4. So it should be the 12. I think I got that right. Yeah, that's the right child of the 9. Okay. The other thing you can do is draw these out. You can draw the tree, 16, right? Here's a 16, then there's a 9 and a 28, and you can draw the whole tree. That's okay too. Perfectly fine to do it that way. Okay. Let's find the left child of 28. So 0, 1, 2. 2 times 28, 2 times 2 is 4, plus 1 is 5. 0, 1, 2, 3, 4, 5. So 26 should be my left child in that case. Okay, I think I got that right. 7, 28, 6, 20. Yeah, I think I got that right. Yeah. Right, child of 9. Yeah, 28. Yeah, we chose a different parent that time. Right. Okay, is valid. Is this thing valid? Okay. So I find the fastest way to do this is to draw it out. So I'm not going to try to, well, can I use this? Oh, let's see if I can actually do this. So if I have a 34, okay, not sure if I can do this very well, and then a 30, right? And then a 29. So we're using a breadth first traversal to build up this binary tree, right? 34, 30, 29, 27, right? 27, and then a 25. I'm not going to go through all this thing, but that's the idea, right? You can build this tree on here. And if you find that anything is bigger than its parent, then we got a problem, okay? So 34 is bigger than its child, is bigger than this child, etc. So I'm just going to try to visualize it without drawing it real quick and see if I can get away with it. But I think this one, so here's left child, right child. Left child and right child of 30 are smaller. Left child and right child of 29 are smaller. And I'm going to take a guess that we're okay. Okay, but it is a little bit of a guess without drawing out the whole tree. But that's the way we go about doing that. Okay. Same kind of thing in reverse for a minimum priority queue. So let's take a bit of a guess at this one. So 31 should be less than its children. 65 and 68 should be less than 40. Or sorry, 40 should be less than 65 and 68. 69 should be less than 75 and 99. So I'm going to take another guess here that that one's okay, but it's a little bit of a guess without working everything out. Okay. And then find parent. I think this might be the last. We got 2 here real quick. To find the parent, got to erase all my scribbles here. Sorry. Erase all. Clear all my drawings. There we go. Okay, great. Okay, so find the parent. To find the parent, we subtract 1 and divide by 2. So what is the position of value 14? 0, 1, 2, 3, 4. Position 4 minus 1 is 3. Divided by 2 is going to be 1. So the parent should be in position 1, which should be item 13. Okay. And indeed, that makes sense for 14. Yeah, exactly. Okay. I think I got that. So 0, 1, 2, 3, 4. Minus 1 is 3. Divided by 2 is 1. 0, 1. So it should be that one right there, the 13. Okay. All right, one more time. Uh, Parent of 11. So 11 is way out here. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. Minus 1 is 8. Position 8 divided by 2 is 4. So 0, 1, 2, 3, 4 gives me the 12. And there's my answer down there. Okay. All right. Onward to the linked list gauntlet. Okay. So this stuff is pretty standard and locked down. So, it's there for reference. Same with this. So we're just looking at the delete code here. So we're trying to delete the head of a list that is linked to this head pointer here. Okay. So these are a little tricky. There are some just, silly coding problems here. So if I grab onto the head and then I say head equals head next, that all looks pretty good. And if the head is null, I return instead of deleting. That one seems a little fishy. So I don't know that that's it. So I'm going to skip that one. If head is not equal to null pointer, then I'm going to say temp equals head next. I'm going to delete the head and then make the new head temp. That actually seems okay at the moment. So I'm going to pick that one. Head is null pointer return. Okay. Delete the head and then advance the head. That's a bad idea because once this is gone, we should never actually advance the head. Sorry, go back to there. And then the last one, just to check, if head is null, return. Okay. Grab the head, then move beyond the head and delete the second thing. That seems wrong, right? So I'm going to go with that one right there. I think that one's probably my best bet. Okay. Couple more, insert at the head. We all probably did this at some point in our homework recently. So let's see what we got. I got a new node. I'm assigning it to newbie. And then I hold on to the old head and make the current head of this class. So remember, this is head pointer is defined right here. Sorry for jumping around on you. So I'm going to make that head equal to the new thing. And then I'm going to say head next equals old head. That looks pretty good. So I'm basically using old head as a temporary pointer, holding on to that so I can grab onto the newbie and then hook up the newbie to the old head. Okay, so I think that's the right answer there. The rest of these look a little suspicious, right? So we got our new node, but newbie next equals head. That's going to create a circular loop. So I'm pretty sure that's my right answer there. So I'm going to go with that one up top. Okay. All right, find. So this one is maybe the more gnarly one. So let's look at these. Let me zoom this up a little bit bigger. Delete, find, so we don't lose our eyes over this one. Oops, I think I jumped forward a little bit. There's the find. Okay, so we're given a value of I. We're going to start at the head, and we're just trying to find the thing and return a pointer to it. Okay, so right off the bat, I see that I'm returning the head pointer. That's not very helpful. I'm looping and thinking about the current node's value, but returning the head. So that's really not the right answer there. Okay. So let's take a look down here. I'm saying, okay, if the head pointer is null, just give up. But otherwise, we've got our current pointer at the head. While the current pointer is not equal to null, and the current pointer or current node's value is not equal to what we're looking for, keep going. So when we get to the end, we are either going to have a null, which means we didn't find it, or we're going to have found the thing that we were looking for. Okay. So this to me looks like a good one. Okay. Because we are returning something all the time. And that's a good bet. Okay. These ones down here, it's never a good thing to advance the head pointer because you'll never get to go backwards again. So that's a little fishy, right? Head equals head next while we're looping on the current node. That's a bad thing. And down here, this one's tempting, but we're only ever returning null. That seems fishy to me. So I think we got our candidate right there. Okay, moving on, delete tail, maybe the trickiest one. We're going to see if I can stretch this out just a little bit, not much. Okay, so we're going to try to find the tail, but in order to delete the tail, we kind of have to stop one before it. So that's your big clue. So when we are looping to delete the tail, we're kind of need to be doing a look ahead, right? So the first one says while temp is not equal to null pointer. So we're not even really looking ahead. We're just going to go until temp becomes null and then delete null. And that's going to crash our program. So that one doesn't look very good. Here we're saying while head next is not equal to null pointer, advance the head. That is never a good idea because we can never really get our head pointer back again. So we should be working with a temporary pointer when we're traversing that thing like that. Okay, so I don't like that one either. Here we're saying, okay, if the head is null, return. Okay, if the head is the only thing, delete the head and set the head to null. I like that. That makes sense. Otherwise, I'm going to say temp gets head, and while next is not equal to null, advance. That's the cool tricky part. So I'm saying, hey, I'm looking ahead to make sure that not the next thing, but the next thing is not null. So that when I get down here, I know I can delete what temp is pointing to. Okay, so I'm deleting what temp is pointing to, which is the last thing. And then I can make that pointer null and return, and I've managed to delete the tail. Okay, so I like that one the best for sure. Okay. All right, so moving on, binary tree traversals. For some reason, these are the ones that I had the most trouble with today when I was rushing. Okay, so let me get to that. So describe the binary tree using breadth first traversal. So actually, this one's not too bad. So breadth first is always going across the rows. So it's going to be 14, 9, 15, 6, 10, right? 14, 9, 15, 6, 10, 3, 7. Okay, so that's our breadth first. That one's a slam dunk. Okay. Breadth first traversal. Describe the binary tree again. Breadth first traversal. Wow. Okay. So 12, 9, 15, 10, 14. 12, 9, 15, 10, 14, 18, 19. So it looks like that one there. 12, 9, 15, 10, 14, 18, 19. Okay. 32, moving along, deleting. So we have to remember when we delete, if we're going to delete the root, for example, or anything, we got to find the next largest thing. And in this case, it's going to be the 12. Okay. So what we want to do is swap those two and then clean up the mess that we created. Okay. So that's going to be easier than anything else we can do. So that means 12 is coming up. 7's going to go down here, and then we got to figure out how to delete the 7. Well, it's kind of easy. We just sort of pull up the 16 into the 12's place. So I got 12 at the top, the 7 was here, it went away, and the 16 came up. So I have something like 12, 4, 16. Okay, so let's see what we have down below. 12, 12, 4, 16. There it is, right? So we don't even really need to go all the way through that thing to get there. Okay. So everybody see that? So we swapped these two, then we got rid of the 7 and let the 16 float up there. So it was the right child of our 12. Okay. Okay. Keep going. Binary trees. One more. So let's delete the root. So this one's a lot easier. So we're just going to swap the 16 and the 17 and then get rid of the 16. So the traversal is going to be 17, 8, 4, 11. Okay. 17, 8, 4, 11. So it's going to be that one right there. 17, 8, 17, 8, 4, 11. And this one's gone over here. Okay. Everybody with me on those? Okay, good. Just want to make sure I'm not putting you to sleep. Okay, AVL, binary trees. Gosh, these are the ones that get me when I'm not paying attention. Okay, so the tree, okay, true or false? Is this tree balanced? Yes or no? The whole tree, okay? So should be easy, right? They can have a difference of 1 at every node. So 1 versus 0, 2 versus 1, 3 versus 1. That's not okay. So that one should not be balanced, that tree. That one is out of balance if it was an AVL tree. So we're going to say, nope, not balanced. Okay, that's a false. Okay, let's try this one. Is it balanced? So 1 and 1, 2 and 3, 2 and 0. That's a problem at 14. Okay, so it's not balanced at 14. So that's going to be a false. Okay. Rotations. Now that we're warmed up about balance, describe the tree after a left counterclockwise rotation applied at 9. So remember that when 9 here. So we're not necessarily balancing this tree. We're just asking you, what is it going to look like if we rotate counterclockwise at the 9? So if you remember, that pulls up the 10 and pushes down the 9. So the traversal is going to be 12, 10, 13, 9. And then I think it'll be 4, 7. Okay. 12, 10, 13, 9, 4, 7. 4, 6, 6, 4, 7. Thank you. 6, 4, 7. Yeah. Instead of 4, 6, 7. Yeah. A little tricky. Okay. Okay. You have no idea how hard it is coming up with these things and not having 2 correct answers. Okay, so that is that one. Tree rotation, another one. So describe the tree after a left rotation at the top node. So left, again, we're rotating counterclockwise, pulling up the 12, pushing down the 7. So it should be 12, 7, 16 comes up here. And then 3, 5, 15. So 12, 7, 16. 12, 7, 16, 4. So let's read it. 12, 7, 16, 4 is down, and then 3, 5. So 4, 12, 7, 16, 4, 3, 5. And then 15 is our last one. Okay. I think I got that right. Okay. Couple more. Right clockwise at the top node. So we're going this way, right? Pulling up the 10, pushing down the 14 and the 16. So we'll have a 10 at the top. Then we'll have a 6. Remember, we hand over the 11. So it's going to be 10, 6, 14. Okay. So 10 comes up, 14 goes down, 6 comes up. So 10, 6, 14. So let's see what we got down below. 10, 6, 14. We got away with a quick one there. Okay. So that's essentially the only answer that's going to fit. Okay. I know these are tedious. 1 or 2 more here. I think yeah, okay. That's probably the last one there. And then back to some code. Okay, so right rotation at the top node. So we're going clockwise. It's kind of weird. It doesn't improve the balance on this tree, but we're just doing it. So we're going to pull up the 6, push down the 7. So the traversal is going to be 6, 7. And then really this subtree doesn't change. So 6, 7, and then we'll have hold on. Yeah, that's right. And then we'll have a 14, 11, 15. So 6, 7, 14, 11, 15. 6, 7, 14, 11, 15. We got to keep going. No, it's 6, 7. Yeah, 6, 7. So that should give us what we need right there. Okay, 10 more. 10 more. We're almost there. Give or take. Question? Yes.
Yeah. So if you're looking for like on the rotation questions, if it asks for like just doing the rotation is different than balancing the tree after the rotation.
Correct. Yeah. And I'll admit that these questions are a little bit like, it's like, huh? Why would I do that rotation? Right. So I kind of came to the decision, for better or worse, like I just needed to focus on the rotation and not necessarily always on balancing the tree. Although I realized it would have been better in hindsight to do that. But yeah, just
There is something on this.
yeah. Thank you for asking that, because it sometimes it gets me too. Yeah. And most of them are at the top node, but some of them are not at the top node. So watch out for that red text. I don't think we had one here. Oh yeah, not at the top node, right? So clockwise at 10. So maybe I even got that one wrong. Did I get that one wrong? I might have got that one wrong. Let's go back and review. At 10 clockwise. So yeah, I think I did that wrong. So it's 14.6. Did I get that? Oh yeah, no, we did that right. Okay, I thought maybe I missed that. Okay, but watch out for that red text there. Okay. Sorry, I digress. Okay, back to the code. So find optimal. This is the whole point about binary search trees, of course. So if we have a root at the head, it's either going to be the value at the current node I'm at, or it's going to be less than to the left, less than or equal to the left, using the convention we've discussed in class, or greater than to the right. But let's look for the landmines, because there's definitely a few here. So this code is always the same. So you don't have to worry about the blue code. It's the same across all answers. It's just sort of doing our initial pointer fix up. So by the time we get to here, this should not be null. So if it's what we're looking for, return true, that's good, right? So otherwise, if it's less than the start, then we got to check two things. Okay. If the left is not equal to null, then return the recursion of, basically the recursive answer to the left subtree. So I'm still looking for I, do that again, and the left subtree. So that makes the recursive call here, and the process continues. If it is null, then we know it doesn't exist, because it can't be in this binary tree. I cannot be here. Okay. So that one's looking pretty good. And then this should just be the mirror opposite of that. Start right is not equal to null. Search right recursively, or it's just not there. Okay. And although, yeah, right. If it's not less than and it's not equal to, then by default, we are going to be essentially greater than. So this is a little bit maybe confusing, but this is essentially the greater than case by default, because we would have returned here and we would have returned here. Okay. So this is like an else down here. Okay. So I think that's the answer. So I'm going to go with that just for the sake of time. Okay. But the rest of these probably have some mild issues with them. Okay. And I'll let you guys kind of drill into that a little bit. Okay, AVL rotations to restore balance. Let's see if I can get this right, because I goofed this up the other attempt I had. So identify the correct rotation sequence or sequence of rotations necessary to bring balance. So this is way too long over here. Okay, 3 versus 1. These are okay, and 1 versus 2 is okay. So we really kind of need to shorten up this branch here. So my first guess is that I would rotate clockwise around the 12, which should push the 12 and the 13 down, making that longer and shortening up this side of the tree. So I'm going to kind of go with that. So that would be a right rotation at 12. Okay, so let's see if that is there. Right rotation at node 12, bringing up the 9. Okay, so I'm going to go with that. I think that's a pretty safe answer. Okay, shortens up that, lengthens that. These subsections are already okay. Right. Okay, do another one. Okay, we want to get this into balance. So this one looks pretty ugly. we've got a 4 down here. And we've also got a 1 and a 3. So I kind of need to do fix up here, and I need to do fix up here. So things are pretty out of whack, right? This is okay, right? And this is okay. 1 versus 0 is okay. But I'm going to guess that I need to do a rotation at the 10, right? To bring up and shorten the left side and lengthen this. But then I'm also going to need to do a rotation at the 17, okay? So that to me seems like a right rotation at the 10 followed by a right rotation at the 17. But let's see what I have down here. So right rotation at the 17, then left. Ooh, gosh. Okay. So right rotation at the 10, bringing up the 6 doesn't seem to be enough because the 17 is still broken. So let's look at starting out at the 17. Just bringing that up doesn't seem to be enough. So what if I rotate at the 17 right, and then I left rotate at the 6 after it comes up? So let's think about what that means. So if I rotate at the right here at the 17, it's going to bring up the 10, push down the 17, and hand over the 11. Okay. So now the 6 is kind of here, holding on to all this stuff. And in order to fix the 6, it looks to me like what we should have done is rotated the counterclockwise at the 6. Okay, now I'm kind of winging it here without drawing a picture, but I'm going to kind of, for the sake of time, take a little bit of a guess. But if I were you, I would probably draw that picture at each of those stages, right? A right rotation at a 17, and then see the 6 there, and then consider the left rotation. I'm a little bit dubious about my answer, though. I'm missing something. I don't know if anybody sees anything, has a strong feeling, let me know there. So we have a right clockwise 17. Does that fix everything? I don't see if it can. Well, we go from a 4 to a 1. That doesn't seem like enough to me. And then the other one, the only other combo rotation is this one down here. So yeah, I'm going to go with that one, okay, just for the sake of time, but I'm feeling a little bit uneasy about it, okay. Okay, down to the last 7 or so here. I think we'll get ourselves wrapped up in 20. So if I want to know what is the performance of this loop, so I'm incrementing by some constant value each time, okay. My conditions are from 1 to n every time, okay. So this is a pretty classic cubic kind of thing, okay? So this is going to be n times n times n, basically, by the time we count up the number of times that thing gets printed, okay? So I'm pretty sure that's going to be a cubic performance assessment. 3 things inside of each other there like that, okay? Okay, now, which of these is the best case? So here we're testing your recollection and your kind of word memory. So this is how we usually see big O linear. This is big omega, and here's another big omega, and here's a big O1. So which of these is a best case lower bound? What's going to be the fastest best case scenario? Okay. So big omega is best case. So it's a matter of remembering what everybody means when they say big omega as opposed to big O, okay? So we're talking big omega, first off, because we're talking best case. And one constant is always going to be faster than something that scales with n. So I'm going to go with a big omega 1 on that one, okay? Okay. Divide and conquer. So this is the one that got me. Select all answers that apply. So don't just pick one because it's not just a pick one thing, okay? So which of the following functions accomplish their task using a divide and conquer strategy, resulting in a worst case performance that is better than linear? Okay. So we're looking for a divide and conquer to do something to find something. So we've got sort of some sorted ascending stuff, and we're trying to see if we can find from 0 to position 7 the value of 9. Now 9 is not in there, which means we're going to have to do an exhaustive search. So this one here is going to say, while start is less than end, keep going. Otherwise, return a false. Okay. So let's see what that does for us. Whoops, I didn't mean to pick that necessarily. Calculate the midpoint. If the target is at that location, say that we found it. Otherwise, if the target is less than that, adjust the end so that it's mid plus 1 and go back around again. Otherwise, adjust the start to mid plus 1. So this one looks pretty good to me. Looks like it's dividing and conquering with a loop. Okay. And then down here we have did find. Again, if start ends up being beyond the end, return false. So it's just another way of having a test for we've gone too far. Calculate the midpoint. If the target is there, we found it. Otherwise, if it's less than the midpoint, return a recursive call where we do essentially the same thing. We just say start and mid minus 1 and target. Okay. So if this, do that, and this is an implied else. Because if we didn't do that and return, then we fall down to here in the else. And so I think that's a good one too, if I look at it. Okay. Okay, and then while end is greater than start, find the midpoint, check to see if I found it. Otherwise, set the end to the midpoint minus 1 and return false. That's outside of the while loop. So here, let's think about this. We're going to set the end to the mid minus and the start to the mid plus, either or. So I think that one is okay. Okay. And I think this is the fishy one down here. If start is greater than end, false. Mid calculation is clearly not correct, so we can leave that one off. Okay. So that one's maybe a little, I don't know, obvious maybe, but we're going to go with that. Okay. All right. Recursion, divide and conquer. Okay. So this is an essay. So these are a little funky, but you can kind of whittle your way down. So we've got a helper function here that's going to print stuff for us. If we get down to an array that is less than or equal to 3. So that's our base case. Okay. So we're going to say, first off, we'll bring our function down. Okay. Okay. Get my prototype, see if I can do this without a compiler. Okay. So we got our base case. We're going to say if end minus start is less than or equal to 3, that's going to be our base case. And we're just going to call our print array function. Okay. So print subarray. So we'll just cheat a little, copy that thing down. Say print subarray here. Actually, I probably should just, that's fine. Okay, array. And we're going to go from start to end, right? That's all we got to do. END and done and return. Okay. So we don't want to go on to do anything else inside of there. Otherwise, we're going to do our divide and conquer. So we're going to calculate the midpoint and do the usual kind of thing. So we'll go down here. We'll say int mid equals start plus end over 2. Start plus end over 2. Okay, that's our midpoint. And then we're going to do the first half. So we'll say do it with array start to mid plus mid. Okay, that's going to be our end. And then we'll say do it. There are mid plus 1 to end, like so. Okay, and that should get it for us. Okay, so this was the easier of the bunch, if I haven't goofed that up. right? Since we're not printing anything in reverse here. Okay. Okay. Recursive step, do your left side before your right. So these are hopefully helpful hints there if you need him to go back and get that thing straight. Okay. So there's that one. Okay, 47. Okay, what are these about? So essentially, we're just, again, poking at your brain to see if you soaked up this idea of logarithms. So, you can kind of see that we're dividing this thing into 1, 2, 3, 4, 5 parts. Okay. And then that becomes a 25, which is another hint. We've divided it by 5 again. So we're essentially doing a divide and conquer by 5, which is going to be kind of a log base 5 kind of answer. So we see some log 5s down here. So what's the question we're trying to answer? Which equation describes the number of rows in the diagram? So the number of rows, okay, 1, 2, 3, right? And we originally had 25 of these things, okay? So probably something like this, right? Log based 5 of 25 is a 2 plus 1 is a 3, right? So I'm going to go with that one right there, 3 rows, okay? If you said n times 5, log 5 for the row count, you got way, way too many rows, obviously. Okay, code assessment. What is this thing? A little out of order. I think I just chucked it here at the bottom. I'll probably rearrange the order of these a little bit. But if somebody gives me an array with a left and right boundary, it's kind of like start and end. So if left is less than right, then find the midpoint, recursively kind of do this and this. And this find index thing is very reminiscent of our quick sort. So if you remember our partitioning function where we sort of have some region and we say, hey, find me a median or a middle point that I can partition around. And we will then just repeat or recursively subdivide, subdivide, subdivide. So this is, if you recall, and you may have to go back and look at your code, is really closest to our quicksort code structure. We do some work at the top, and then we whittle our way back down, which is kind of the opposite of the merge sort there. Okay. Okay, 2 more. All right, so divide and conquer, finish implementation so that it returns the product of all members of the array from position start through the end inclusive. So we're given an array, start and end. If end is equivalent to start, then we should just be able to return either the start or end position, right? There's nothing, it's like we found an odd number of things. We can't do a multiplication. Otherwise, let's calculate the midpoint as always, and then return the product of the left times the product of the right, okay? So this is really the insight that kind of unblocks it. So we want to go from start to mid times the array of mid plus 1 to end, okay? So we're going to multiply whatever the cumulative product is for that recursively times the cumulative product of that, okay? And the last one, oh, 2 more, sorry, 2 more. Given the set 7, 5, 6, 1, where 7 is chosen as a partitioning value, so this is again a quicksort thing. What is the interim ascending quicksort result after just the first partitioning? So we're going to partition around the 7. We're not sorting, we're just sort of trying to say what's on the left and what's on the right of the 7. Well, as it turns out, everything's on the left hand of the 7 for an ascending sort. So we're really looking at this answer right here. Okay. And obviously we got to remember what it means to partition. That's obviously the main point of that question right there. Okay, and then the last question is just what's the minimum of the binary search tree shown? So that's not a hard one. So the minimum of 10 of this whole tree is going to be 8. So our answer there is going to be 8. And let's just double check and see if we answered all the questions. I don't have a really good feeling. I feel like I rushed and probably got 1 or 2 things wrong, but let's see how I did. Okay. Okay. I got an 84 out of 100. That's really not, that's worse than I was thinking. That's pretty bad.
The essay question?
Oh yeah, maybe. Yeah, still not good. So I got I got that one wrong. Okay. Well, it's nice to see that not everybody is as brilliant as they seem to be. So yeah, certainly the moral of this story is making sure you go back and check. Yeah, I remember I was guessing on that one pretty quickly rather than doing the hard work. But yeah, need to go back and check that one. We kind of felt like that was maybe off. 2, maybe that was it. And then my essay. Nope, I missed that one too. So that one I was guessing I should have drawn out the tree on that one. Hint, draw the tree out in breadth-first order. I sort of did a guess. Did a guess there as well. Shouldn't have rushed. Should have done the tree. So you can kind of see there, if this was a min priority tree, the thing that was wrong was what? 65. See that 64 broke it for us. Yeah, I put it all the way at the end and I kind of got cocky and I was like, oh, I'm sure it's not over there. But yeah, that was the thing that broke it for me. So I really should have drawn that thing out and I would have done better there. So just a little bit of rushing. 2 of 2, 2 of 2. No huge surprises. Got the code right. Hopefully I got my rotations right for once. AVL, 2 of 2. 2 of 2. Okay, good. Doggone it. Is that the one I was confused about? What did I do wrong there? Rotate, left rotation at the top node. So if I rotate to the left, 12, 7, 16. 12, 7, 16. Oh, okay. So 12, 7, 16. The next thing that I should have had, if the 7 was down here, should have been 3, 5. 12, 7, 16, 3, 5. 12, 7, 16, 4. Huh. Okay. Does anybody see it? All right, let's do this one. Sorry. I know we're not quite there. Yeah, go ahead. Yes. Right. Oh, yeah. So the 15 is on the level of the 3 and the 5, or no, of the 7. So 15 is at level 2, 7's at level 1. Yeah, so it should be 3, 5, 15. No, yeah, we had that. So that's the wrong.
That's a level of 4. It'd be 4, 15, and 3, 5.
4, 15, and 3, 5. Okay. All right. Oh, okay. Oh, there. Yeah. Okay. Yeah. So yeah, again, moral of the story. And another one. Draw them out. Gosh. Yeah, no, my favorite way to do it is draw it out. I hate trying to figure them out in my head. So that's definitely a shame on me for that one. So let's see. We got a couple. 40's okay. I hope I got the code stuff right. Okay. 2 of 2 on that one. Okay. Oh! So embarrassing. Okay. Don't, yeah, do as I say, not as I do. Isn't that the famous saying? Okay. And don't rush. Don't rush. Let's see if we did anything else. Okay. Okay, got that one. Oh yeah, that's okay. Got that one okay. Got that one okay. Okay. All right then. Okay. And got that one. Whew, at least I got one. Okay. All right. Well, teaching moments, as they say. All right. I'm going to leave you with that then. Let me know if you have any questions. I'll go over, of course, and check and make sure that the answer key is okay, but I think it's probably okay. So good luck. Let me know if you have questions. I'll see you all on Thursday and come in a little early and we'll get ourselves set up. All right. Thanks, everybody. Appreciate your patience. We'll see you on Thursday. Mm,